Hello my friends and welcome back to KrossUSA channel. Today, we're taking you on an incredible journey through 5 of the most impressive industrial processes that are shaping our world. So let's explore how the world's leading companies are pushing the boundaries of manufacturing excellence. Let's kick things off with something truly spectacular. The steel production powerhouse that is Altos Hornos de Mexico, or AHMSA as it's commonly known. This Mexican steel giant has been forging the backbone of infrastructure for decades, and their Monclova facility is nothing short of impressive. With an annual production capacity of over 3.5 million tons, AHMSA operates one of Latin America's most sophisticated integrated steel complexes. What makes AHMSA's process fascinating is their fully integrated approach. It all starts with their massive blast furnaces. These towering giants reach temperatures of over 3,000 degrees Fahrenheit. The process begins with carefully prepared raw materials. Iron ore pellets, coking coal, and limestone are precisely measured and loaded into the furnace top. The magic happens when heated air, enriched with oxygen, is blown through tiers at the furnace base. This creates the perfect chemical storm, where carbon monoxide reduces iron ore to molten iron. The blast furnace operates 24/7, and here's what's remarkable. Every 4 to 6 hours, they tap the furnace to release molten iron at temperatures around 800 degrees Fahrenheit. This liquid iron, glowing like liquid sunshine, flows through carefully engineered channels into massive torpedo cars that can hold up to 350 tons of molten metal. Now here's where the real transformation happens. That molten iron heads to AHMSA's basic oxygen furnaces, or BOFs. These aren't your average furnaces. They're 200-ton capacity vessels that perform metallurgical magic. Pure oxygen is lanced into the molten iron at supersonic speeds, burning off excess carbon and impurities. The process is so intense that the temperature actually increases to over 3,000 degrees Fahrenheit. What's brilliant about AHMSA's setup is their computerized control systems that monitor every aspect, from oxygen flow rates to lance positioning. Skilled operators can adjust the process in real time, ensuring each heat of steel meets exact specifications. The entire conversion from iron to steel takes just 45 minutes, but the precision required is extraordinary. The liquid steel journey continues to AHMSA's continuous casting machines, and this is where modern engineering truly shines. The molten steel flows through a tundish into water-cooled copper molds, creating solid steel billets, blooms, or slabs in one continuous process. No more old-fashioned ingot casting here. This technology produces superior quality steel with consistent properties. Their rolling mills are equally impressive. The hot rolling mill can process slabs up to 250 millimeters thick, using massive rolls that apply pressures of thousands of tons per square inch. The steel passes through multiple stands, each reducing thickness while increasing length. Temperature control is critical. The steel must maintain specific temperatures through each pass to achieve desired mechanical properties. AHMSA's commitment to quality is evident in their state-of-the-art testing facilities. Every batch undergoes rigorous testing, from chemical composition analysis to mechanical property verification. Their products supply automotive manufacturers, construction companies, and energy sector clients across North and South America. It's this attention to detail and massive scale that makes AHMSA a true industrial powerhouse. Now let's shift gears to precision manufacturing with an absolute beast of a machine, the KZTS 1K665 F3X 7000 heavy-duty CNC lathe. This isn't your typical workshop lathe, folks. We're talking about a machine that can handle workpieces up to 7 meters long and 1.6 meters in diameter, with a maximum turning weight of 25 tons. The spindle delivers an impressive 250 kilowatts of power, with torque ratings that can handle the most challenging materials. The heart of this machine is its sophisticated CNC control system. We're looking at a multi-axis system that can execute complex machining programs with incredible precision. We're talking about positioning accuracy within 0.01 millimeters over that entire 7-meter length. The control system features advanced interpolation algorithms that ensure smooth toolpaths, even during the most complex contouring operations. The programming interface is remarkably user-friendly, featuring graphical programming tools that allow operators to visualize toolpaths before execution. Real-time monitoring systems track everything from spindle load to cutting temperatures, with automatic adjustment capabilities that optimize cutting parameters on the fly. The machine can store hundreds of part programs, making it incredibly versatile for batch production or custom one-off projects. Watching this machine work is truly mesmerizing. The tool turret can hold up to 12 different cutting tools, automatically selecting and positioning the appropriate tool for each operation. The machine excels at heavy-duty roughing operations, capable of removing material at rates that would challenge smaller machines, yet it can switch to finishing operations with surface finishes measured in micro-inches. The coolant system is engineered for these demanding applications. High-pressure coolant delivery ensures optimal chip evacuation while maintaining cutting temperatures. The machine's rigid construction minimizes deflection, crucial when machining large, heavy components, where precision is paramount. This KZTS lathe serves industries requiring large, precision-machined components. Think power generation turbine shafts, marine propeller shafts, large hydraulic cylinders, and aerospace components. The combination of size capacity, precision, and automated operation makes it invaluable for manufacturers who need to machine large components to tight tolerances efficiently and reliably. Welcome to one of America's most impressive manufacturing facilities, United Launch Alliance's 1.6 million square foot rocket manufacturing complex. This isn't just big, it's aerospace industry big. ULA, the joint venture between Boeing and Lockheed Martin, assembles the rockets that launch our most critical national security and scientific missions into space. The facility spans multiple buildings, each specialized for different aspects of rocket production, from component fabrication to final integration and testing. The scale is breathtaking. We're talking about clean room environments that can accommodate rockets over 200 feet tall, with crane systems capable of precisely positioning multi-ton rocket sections with millimeter accuracy. Let's dive into how they build these incredible machines. ULA manufactures both Atlas V and Delta IV rockets, each requiring different manufacturing approaches. The process begins with precision machining of aluminum and steel components using some of the world's most advanced CNC equipment. Tank sections for the rocket bodies are formed using specialized techniques. Imagine forming paper-thin aluminum sheets into perfect cylindrical sections that must withstand the incredible pressures and temperatures of launch. The welding processes are extraordinary. We're talking about friction stir welding for aluminum components, creating joints stronger than the base material. Every weld undergoes rigorous non-destructive testing using ultrasonic and X-ray inspection. The propellant tanks must be absolutely perfect. A single defect could be catastrophic. The integration process is where engineering precision meets choreographed excellence. Rocket stages arrive from various suppliers and undergo meticulous inspection before assembly. The integration facilities feature specialized tooling that supports multi-ton rocket sections, while allowing technicians complete access for installation of countless subsystems. Each rocket contains thousands of components, from complex avionics systems to precision-machined engine components. The electrical integration alone involves hundreds of connectors and thousands of wires, all precisely routed and secured. Environmental control systems maintain specific temperature and humidity levels throughout assembly, ensuring optimal conditions for both the hardware and the technicians. Before any ULA rocket leaves the facility, it undergoes exhaustive testing. We're talking about complete electrical system checkouts, pressurization testing of all fluid systems, and verification of every single subsystem. The test equipment itself is impressive. Specialized test sets that can simulate launch conditions and verify that every system performs exactly as designed. The quality assurance process involves documentation of every single component, every process, and every test. Traceability is absolute. They can tell you the manufacturing history of every bolt, every wire, and every weld in the rocket. The final stages involve careful packaging and preparation for transport to launch sites. These rockets are designed for reliability above all else. ULA has an incredible success rate because of the meticulous attention to detail throughout this entire manufacturing process. From raw materials to launch pad, every step reflects the precision and quality that space missions demand. Let's dive into something that's absolutely fascinating: the world of high-speed tube manufacturing with Formtech Group's incredible 24-inch tube mill featuring the revolutionary Yoder cage forming system. Now, you might think tube making is straightforward, but when you're producing precision tubes at industrial speeds, it becomes an engineering marvel that combines metallurgy, precision mechanics, and advanced automation. Formtech Group has been innovating in metal forming for decades, and their tube mills represent the pinnacle of roll forming technology. This particular 24-inch mill can produce tubes from 1 inch to 24 inches in diameter, with wall thicknesses ranging from lightweight architectural applications to heavy structural components. The production speeds we're talking about here can reach up to 400 feet per minute. That's incredibly fast for precision tube production. Now, here's where things get really interesting: the Yoder cage forming system. Traditional tube mills use a series of roll stands that gradually form flat strip into round tube. But the Yoder system revolutionizes this approach. Instead of multiple forming stands, the Yoder cage uses a series of precisely positioned rollers arranged in a cage-like configuration that forms the tube in fewer steps with superior control. The genius of this system lies in its adjustability. The cage assembly can be quickly reconfigured for different tube sizes without extensive tooling changes. Each roller in the cage is precisely positioned and can be adjusted independently, allowing for incredibly fine control over the forming process. The system uses servo-driven adjustment mechanisms that can position rollers to within thousandths of an inch. What makes this particularly impressive is the forming forces involved. We're talking about pressures of thousands of pounds per linear inch, yet the system maintains dimensional accuracy that's measured in thousandths. The cage design also provides better support for the forming tube, reducing the risk of deformation or quality issues that can occur in traditional mills. Let's follow the process from the beginning. It all starts with coiled steel strip that's been precisely slit to width. The entry section of the mill features sophisticated uncoiling and straightening equipment. The strip passes through leveling rolls that remove any coil set. That's the curvature that develops when steel is coiled. This is crucial because any irregularities in the strip will translate directly into tube quality issues. The strip then moves through edge conditioning stations that can perform various operations: edge trimming for precise width control, edge rolling for improved forming characteristics, or even edge welding prep when required. The mill features dancer rolls and tension control systems that maintain consistent strip tension throughout the forming process. This tension control is critical. Too little tension and you get wrinkles or waviness. Too much, and you can cause dimensional problems or even strip breakage. The entry speed can be synchronized with the forming mill, allowing for smooth transitions when starting new coils or when running continuous operations with coil joining systems. As the strip enters the Yoder cage, the magic of tube forming begins. The strip is gradually formed from flat to round through a series of precisely controlled forming stages. The cage system allows for more gradual forming angles, which reduces stress in the material and produces superior tube quality. The forming process is so well controlled that the system can handle a wide range of materials, from soft aluminum to high-strength steels. The welding process is equally impressive. Most tube mills use high-frequency induction welding, where the tube edges are heated to welding temperature by induced current, then squeezed together by welding rolls. The Formtech system features advanced welding controls that automatically adjust power levels based on tube size, wall thickness, and production speed. The weld quality monitoring systems use both visual inspection and ultrasonic testing to ensure every weld meets specifications. What's particularly clever is the weld seam tracking system. It automatically adjusts the welding parameters to compensate for any variation in strip width or edge condition, ensuring consistent weld quality throughout the entire length of the tube. After welding, the tube passes through sizing stations that bring it to final dimensions. These aren't just simple sizing rolls. They're precision-engineered roll sets that can control not just diameter, but also roundness and concentricity. The sizing forces are carefully controlled to avoid oversizing, which can cause dimensional instability. The finishing section can include various operations depending on the tube specifications. Straightening systems remove any bow or sweep that might have developed during forming. Some configurations include online testing equipment that can perform dimensional checks, wall thickness measurements, or even non-destructive testing of the weld seam. The mill also features sophisticated cutoff systems that can produce precise lengths. These systems use servo-driven saws that can cut while the tube is moving, maintaining production speed while delivering accurate lengths. The entire mill is controlled by advanced automation systems that integrate every aspect of the operation. The control system can store hundreds of different tube specifications, automatically adjusting all mill parameters when changing from one size to another. This includes roll positions, forming speeds, welding parameters, and sizing settings. Real-time quality monitoring is built into every aspect of the process. Dimensional monitoring systems continuously check tube diameter, wall thickness, and roundness. The system can automatically adjust process parameters to maintain quality or alert operators if specifications drift beyond acceptable limits. Production data collection and analysis capabilities provide detailed reporting on productivity, quality trends, and maintenance requirements. This data-driven approach allows mill operators to optimize performance and predict maintenance needs before problems occur. The versatility of this FormTech tube mill system serves multiple industries, from structural steel for construction to precision tubes for hydraulic applications, from automotive components to HVAC ductwork. The combination of speed, precision, and flexibility makes it an ideal solution for manufacturers who need to produce various tube sizes and specifications efficiently. The Yoder cage forming system's rapid changeover capabilities mean manufacturers can respond quickly to market demands, producing smaller batches economically while maintaining the efficiency needed for large volume production runs. Welcome to the ultimate precision machining showcase, the complete manufacturing of a two-cylinder crankshaft on the remarkable Niles N20MC 5-axis turn/mill center. This isn't just machining. This is sculptural precision applied to one of the most critical components in any internal combustion engine. Our journey begins with a carefully selected 42 CRMOV4 steel forging. This isn't just any steel. It's been specifically heat-treated to achieve the optimal balance of strength, toughness, and machinability. The forging process has already provided the basic crankshaft shape, but we're still talking about machining tolerances measured in thousandths of an inch. The workpiece setup on the Niles machine is critical. The crankshaft is held between centers with additional support from steady rests that can automatically adjust position as the part rotates. This is essential because crankshafts are inherently unbalanced. Those offset crank throws create dynamic forces that would cause vibration and poor surface finish without proper support. The machine's 5-axis capability means we can access every surface of the crankshaft without repositioning the workpiece, which is crucial for maintaining accuracy between related features. The machining process is a carefully orchestrated sequence of operations. We start with rough turning of the main journals. These are the surfaces that ride in the engine's main bearings. The Niles machine's powerful spindle handles the interrupted cuts as the crank throws past the cutting tool, maintaining consistent surface speeds despite the varying geometry. Next comes the rod journals, the offset surfaces where connecting rods attach. This is where the 5-axis capability really shines. The machine can tilt and rotate to access these angled surfaces while maintaining optimal cutting conditions. The programming is incredibly sophisticated. Every tool path is calculated to maintain constant chip load despite the complex geometry. Between roughing and finishing operations, the crankshaft undergoes stress relief heating cycles. The Niles machine can accommodate these interruptions seamlessly, resuming operations with perfect positional accuracy thanks to its absolute encoder systems. The finishing operations are where the Niles machine's precision truly shows. We're talking about surface finishes measured in microinches, with dimensional tolerances of plus or minus 0.0002 inches on critical bearing surfaces. The machine uses specially designed cutting tools with precise geometry and advanced coatings that can maintain cutting-edge integrity throughout the entire machining cycle. Oil passages are precisely drilled using the machine's integrated drilling capabilities. These aren't just holes. They're precisely positioned and sized channels that ensure proper lubrication flow throughout the engine. The 5-axis capability allows for compound angle drilling that would be impossible on conventional machines. The final surface finishing passes use carefully controlled feeds and speeds, with flood coolant systems maintaining optimal cutting temperatures. The machine's vibration damping and thermal stability ensure that these critical finishing cuts produce the surface quality that modern engines demand. Every completed crankshaft undergoes rigorous inspection using coordinate measuring machines that verify every dimension. The Niles machine's capability to complete all operations in a single setup means fewer opportunities for error accumulation, resulting in superior part-to-part consistency. The finished crankshaft represents hundreds of precisely controlled machining operations, each contributing to a component that will deliver reliable performance for hundreds of thousands of engine revolutions. This level of precision manufacturing is what enables modern engines to achieve the performance, efficiency, and reliability that drivers expect.